Hey guys, this is Math 148, section 13.1. Thought you guys might be happy because this section there's no integrals, no derivatives. We're taking a very small break from integrals and just looking at rectangles. Rectangles, I know, it's exciting. So in this section, we are beginning the topic of how to estimate the area under a curve. This is actually where integration really kicks into play. We use integrals to find the area under a curve. But before we use integrals, they're going to introduce this idea of finding the area under a curve in a simple way, under a curve. So suppose we have a function that looks like this, right? It's some wobbly thing, and we want to find the area between, let's say this is 2 and this is 3, and we actually want to find this whole area under the curve, right? This area. Well, in the next section, in 13.2, we're going to find this area using integrals. But for this section, 13.1, we're going to practice finding the area, that's an A, using rectangles, or these little boxes. So the idea, and this is a quick introduction, then I'll do a problem, is that we're going to divide an interval, like from 2 to 3. Let's divide it into these even intervals, and then we're going to draw boxes over each interval, and we're going to approximate the area using the area of these boxes, like this. Here, last box. Come on, box. Like that, maybe. So we're going to use these areas of these boxes to approximate the area under the curve. You can imagine it's not particularly exact because boxes will never perfectly match exactly what's going on with the curve, but it's sort of close. So here's the first example. Let me look at question number 3 in this section, 13.1, and it says, approximate the area under the curve for this function. F of x is equal to 9 minus x squared, and we're going to be approximating the area under the curve from x equals 1 to x equals 4, x equals 3, sorry, and we're using 4 sub-intervals. That means we're going to be using 4 little rectangles, sub-intervals. Okay, so one thing you can think about before you draw anything, you're thinking, some of you may see this immediately as a parabola because it's quadratic and it has a squared term there. So this is a parabola that faces down because of this negative in terms of the x squared. But it's okay if you didn't see that right away. Here's our x equals 1, and here's x equals 3. We're going to divide this area, which is a total distance of 2. That's 3 minus 1 is 2. We're going to divide this into 4 subintervals. So the first thing you want to do is figure out how wide is each interval. Well, the width is going to be, in this case, 2, which is the total distance, divided by 4 intervals, which is 1/2. Okay? And they will all be about this complicated. So you could have probably seen this right away. You could have said, well, I could divide it in half, and that's x equals 2. And then right there is 1.5, and this is 2.5. So now we have our intervals, right? There's 1 interval, 2, 3, 4. So the book also says for this problem, we're going to use right-hand intervals. Right-hand intervals, and this becomes important. Right hand. So we're going to use the right endpoint. So the right endpoint, here's the first interval, right, from 1 to 1.5. The right endpoint is this part, right, because it's on this side, it's on the right-hand side. So this is our first endpoint. So the second endpoint is the second interval. So interval 1, that's endpoint 1. Interval 2, endpoint 2, 3, and 4. Okay, so this is little endpoint 3 and endpoint 4. So this is what we're doing next. Okay, so we know we have these intervals. Oops, sorry, need a better color. We know we have these intervals. Here's our, and I'm going to make x and f of x. I'm making a little column. So, wait for it. So we have 1, I'll make 3. This is the x, this is the same picture I had before. 1.5. 2.5. So you make a column here, and on this column is the end points. So in this case, You say, well, the first endpoint is 1.5, the second endpoint is 2, the third endpoint is 2.5, and the final endpoint is 3. And again, this was my picture. First endpoint, second endpoint, third, and fourth. And I got that because I'm trying to estimate the function between 1 and 3, and I'm breaking it into 4 even intervals. Okay. So now we evaluate the function, which was equal to 9 minus x squared at each one of these points. So at x equals 1.5, I say, well, that function is 9 minus 1.5 squared. That's 6.75, so I put that in my calculator. I evaluate it at 2, so I have 9 minus 2 squared. That's 5. 2.5, the answer is 2.75. Just skipping ahead here. And at 3, 9 minus 3 squared is 0. So this is why we do this. Now we're saying, well, to approximate this first interval, I'm going to make a rectangle that is approximately 6.75 high. So imagine, at this point, the function f of x is equal to 6.75. So suppose you knew nothing else about the function. You say, well, I'm going to estimate this area by a box here that's 6.75 tall. Okay, so the height is 6.75 because I know that this point right here hits the function at 6.75, and it's 0.5 wide because 1 to 1.5 is 0.5. Okay, for the next box at 2, so you imagine some imaginary function, it hits 2 at 5. We'll say this is f of 2 is equal to 5. So we know now we have a box here that is 5 tall, and it's still 0.5 wide. At 2.5, we know that the box is 2.75 tall. Here. That is 2.75 in height. And again, the width of the box is 0.5. I'm making these little boxes to approximate the area. And at 3, the height of my box is 0. I like that box. Right? It is 0 tall. That's a little flat box. It's not even a box. It's a flat thing. So now we're going to find the area of these boxes and add them up. So, whoa, that area plus, I'll do a different color area, this area plus, ooh, it's ugly, this one plus purple. Oh, there's no purple. I ran out. Okay, so here's how we add the areas. Our approximate area, which is the goal of this problem, is to find the approximate area under the curve. We don't know what the curve looks like, but we know it does something, and then boom, it hits here, and then goes, ah, boom. Actually, we do know it's a parabola, but you see my point. Boom, like that. So this is the approximate area. Now we just add the area of the rectangles. So this area is going to be 6.75 times 0.5 times. So you have 6.75 times 0.5, that's the first box, plus 5 times 0.5, that's the second box. I'm adding areas. Area is base times height is the formula for area. This box is 0.5 times 2.75, and this final box is the width is 0.5, and it's 0 tall. So your total answer for the area should be 7.25. 7.25. And again, I'm calculating each function evaluated at the right-hand endpoint, and then I'm using that for the height of my box, and then adding up the various heights of the boxes. I think I have a picture for you, this one. So what I did, again, we're going from 1 to 3. So we said we're dividing this into 4 intervals. So we know that each interval, there's 1, 2, like 3, 4 intervals, and we wanted right-hand endpoints, and that matters because I know that I have to take the function evaluated at that point. So this is the equation, by the way, in case you guys didn't figure that out. So the first box was this tall, and then we added a box. We started at 2, and we said that's this high, 5 tall. We added the box at 2.5, was only that tall, and the box at 3, oops, there's no box at 3. So we're actually not getting this space. And then we added up all of the areas, Ding. Oops, that's right, I can't add the areas on this box because it'll just add the little rectangles. But the total area of boxes, equals 7, it's a 7.25. So we're making little boxes and we're adding up the area. Let's do another one. Okay. Same thing, question number 5. So we have another function. We're saying f of x is equal to 4x minus x squared, and we want to go from x equals 0 to x equals 2, and so that's our distance, and we're going to use 2 sub-intervals. Yay! I'm saying yay because we're going here, x equals 0 to x equals 2, and we're going to divide this into 2 intervals, so the total distance is 2 minus 0, which is 2. You guys probably saw that. We're dividing that by 2 intervals, so put 1 here. Basically, each interval is length 1. So the other thing about this problem is now we want left-hand endpoints. And the endpoint direction matters because, as you can see from this other picture, if you use right-hand endpoints, you get this line, dot. If you use left-hand ones, you get a box that's a different height. So whether or not you're doing right-hand or left-hand endpoints matters about how tall your box is. So the endpoints we're going to use left-hand endpoints. So here's our first interval. We're going to use this point right there. So here's x equals 0 is our first endpoint. Say x, 0. And then x equals 1 is our second endpoint. And we're only doing 2 intervals, so we're done. F of x, here, when you plug in 0 into this equation, you get 0, right? 4 times 0 minus 0 squared. When you plug 1 into this equation, you get 4 times 1 is 4, minus 1 is 3. So that tells you, if we're approximating the area, our first box, it goes from 0 to 1, and it's 0 high. You gotta love these, right? So the area is equal to, the box is 1 wide plus 0 tall, plus the second box here is 1 wide and 3 tall. 3. So the answer is 0 plus 3 is 3. The approximate area is 3. And I think I drew this one out too. So here's question number 5. We're going from 0 to 2. This is what we just did. We divided it into 2 intervals. So this is the first interval is here. We picked the left-hand endpoint, so that was the first endpoint. That's the second endpoint. And now we're drawing boxes. So the first box is flat. There, that's a box. The second box is, second box is only as tall as the function right there. So we take f of 1 and we only get that height. And that is right here, right there. That's the function. So our approximate area is the area of this rectangle plus this flat little rectangle, and we said that was 3. So you can see that this rectangle business for approximating is not very good because we are not getting this area and we're not getting this area. So when it comes right down to it, integrals are better at estimating area. So you should be happy for that when we get to section 13.2. I don't think you're going to be that happy though. You might be. I don't know. All right. One other thing I want you to look at for this section. File new. Don't save. So here's a graph, or here's a summation notation. This is a final topic. Summation notation. Some of you saw this in statistics. So here's question number 17. Suppose we have this capital, looks like an E, but it's actually a capital sigma. It's a Greek letter, sigma. And it looks like this sigma. J goes from 2 to 5, and we have this j squared minus 3. So the question asks you to find the value of the sum. Essentially, this is what we're doing with the rectangles. We're adding a bunch of things. Find the value. If you're wondering, why is this summation in this section? It's because you're summing the area of the rectangles. But what you do is you take this variable and you let the variable go from 2 to 5. So in this case, we're going to let j equal 2, j equal 3, j equal 4, and j equal 5. And then when j equals 2, we get 2 squared plus 3, right? I'm plugging j equals 2 there. Plus, this summation means plus, big capital sigma. And then j equals 3, we get 3 squared minus 3. Oops, it's minus 3. Minus. Plus, now we're doing j equals 4. 16 minus 3. I jumped ahead. 4 squared. Plus, so you're always adding. It's always plus. 5 squared minus 3. So you do this all out. You get 4 minus 3 is 1. That was a minus. Plus 9 minus 3 is 6. Plus 16 minus 3 is 13. Plus 25 minus 3 is 22. So all of this equals, look at this, 7 plus 13 is 20, plus 22 is 42. What? It's the answer to the ultimate question of life, the universe, and everything. It's a little Douglas Adams joke. So again, this section, what we're doing is we are finding the area by estimating the area by finding the area of these boxes and adding them all together, and you want to pay attention to whether or not you're using left-hand endpoints or right-hand endpoint, because it's going to depend on how tall your box is. And then we're going over this summation notation, so you should be able to look at something like this and turn it into a number. No derivatives, no integrals.